Good morning, guys. Hello, and welcome to another session of Rockville High School Chemistry Distance Learning. This is the session for the week of May 4th to May 10th. This is session 5, and today we are going to talk about acids and bases. So, the objective of this lesson are a little bit complex. And if you really look at these objectives, you will not see the word acid and bases anywhere. But acids and bases are quite of interlinked with the objective that we are going to work on today. So let me go over the objectives for this week. The Earth's surface is a complex and a dynamic set of interconnected systems, principally the geosphere, the hydrosphere, the atmosphere, and the biosphere. So these are my four spheres that you will be hearing this word again and again, and they will interact over a wide range of temporal and spatial scales. All these, let me go back. All of the Earth processes are the result of energy flowing and the matter cycling within the and among these systems. If you really know about the energy flowing that we talked about the last week that we have been working on those. So these acids and bases that we are going to do today will be important for the different spheres that we are going to talk over the weeks. The second objective is the climate change can occur when certain parts of the Earth systems are altered. Changes in the atmosphere due to human activity have increased carbon dioxide concentration and thus affect the climate. So, increase in the carbon dioxide, how does it affect the concentration of the climate? How does it affect the oceans and the atmosphere? That is our ultimate goal, and that's what we are going to do over the coming weeks. And for that, you definitely need a little bit of knowledge of acids and bases. The key terms and the equations for this lesson will be Bronsted-Lowry acid, Lewis acid, Bronsted-Lowry base, amphoteric, pH, proton donor, proton acceptor, and the indicator. There will be two assignments for this week. We'll be posting them on Google Classroom. There's a Google form answering the question on the properties of acids and bases. Here we go. This is the assignment. And the another assignment that I'm going to talk to you about is there'll be a FET simulation, and you will be answering the questions after you do the FET simulation. Here is the FET simulation. I can show you what the simulation look like soon. And so this is the FET simulation. Let me go over it. Control C and Control V. So you will be working on this FET simulation, and after you work on this FET simulation, you will be answering the questions on the Google form for acids and bases. This is the Google form that connects to the FET simulation. So again, as I was going back and forth to the screens, let me go over the assignments over once again. Both these assignments are due on the 10th. The assignment is the two Google forms. One is with the that relates to the slideshow that I'm um, video recording about the properties of acids and bases, and the other one is based on the FET simulation that I just showed you the link. So do the FET simulation and then answer the questions again on the Google form. I don't need this guy. Here we go. So let me introduce the acids and bases to you. Acids and bases are all around us in the everyday product that we use. Citric acids are like citrus fruits, like oranges, the lemons, which are required today in COVID 19. You need to boost up your vitamin C. They are sour in this taste. And why they are sour? It is because of the citric acid. Bleaches, soaps, and other cleaning supplies are all the bases. They are high in demand these days. I am not able to get Clorox anywhere. And you will be surprised, even the DNA that makes up your body is the deoxyribonucleic acid, is again an acid. So, what is an acid and what is a base? That's what the main question is. And let me go back to that. And how is the pH determined? Those are the two things that we are going to focus on. So, acids and bases play a central role in much of the chemistry of what affects our daily life. And you can see the daily products here. Your body needs acids and bases to function properly. Vinegar, carbonated drinks, and foods such as citrus fruits, they contain all of them, they contain acid. And if you go back and see, they or like feel the taste, they're all a little bit sour. So acids are sour. The electrolyte is in the car battery, that is an acid again, that is sulfuric acid. Most manufacturing processes use acids and bases. They are important in one of the process, whether they are your sneakers, your cell phones, the way they are processed, all of them are acids and bases have been used. So, what are the properties of the acids? Acids have several common properties. Let's go over the properties. They are sour in taste, they are corrosive, that means they will harm your skin. Acids react with the indicators to produce a predictable change in the color. So, if you dip up indicator like the pH paper in a solution, it will change the color. So, and you can figure out whether it's an acid or a base. And like bases, acids can conduct electricity. And why do they conduct electricity? Because they are electrolytes. Both of them are electrolytes and they can conduct electricity. Bases. Unlike many common acids, typically bases are not in our food. They are in the cleaning supplies. Like you see these guys here. Some foods, such as the egg whites, are slightly basic though. Medicines like antacids are basic. If you really see the word antacids, so these, the Tums, it is working against the acid, is making it neutral. That's why it is when you have acidity, you have them because it will neutralize the acidity in your stomach. Bases are important in many types of cleaning materials. Clorox, not been able to find Clorox in Whole Foods, Amazon, um, Costco. They were totally out during COVID-19. Bases also have several common properties. They are slippery or soapy. They are bitter in taste. They also conduct electricity because they are electrolytes. So, this is the property that is common to the acids. And they also change the color of the litmus paper. Though it is different, that the basis color change the color of the litmus paper from red to blue, and the acids do blue to red. They are slippery because they're soapy because they will be reacting with the oils and will be cleaning the surface. But of course, they have a sour in taste or bitter in taste, but in the lab, we never taste anything. So there have been different definitions of acids and bases, and that's what I'm going to concentrate on now. Um, and it kept on growing as we kept on having more knowledge about acids and bases, and more substances were discovered, and our understanding kept on growing. Acid is a substance that releases the hydrogen ions in water. This is a hydrogen ion, it's either charged atom of hydrogen is an ion. So anything that releases an H ion in the water is considered to be an acid. So common theme in most the acid is element hydrogen, water, and the hydrogen ion. And you will see this hydrogen ion here or the hydronium ion, this H3O plus, we call it the hydronium ion. Whether it is a proton, H ion, or hydronium, it means the same thing, the H ions, different terms. The first definition of an acid was given by a Swedish scientist, Svante Arrhenius, and you will hear this term over and over again as you proceed with your chemistry knowledge. So, what he defined as an acid in terms of hydrogen ions. Arrhenius acid produces hydrogen ion, which in water becomes a hydronium ion. So, H plus and the water combining to give you a hydronium ion. So, the definition of Arrhenius acid was if anything that can give a hydrogen ion, like HCl in the water, giving you H ion, and this H ion combining with the water, combining and giving you a hydronium ion is considered to be an acid. So anything that is producing an H ion will be an Arrhenius acid. But it only applies to the solution with the water. So water was an important thing in Arrhenius definition. Sometimes when talking about acids, the term proton, like I talked earlier, hydrogen ion, and the hydronium ion are all used together. So H plus, H3O plus, or a proton, they're the same thing. A proton refers to the hydrogen ion. A hydronium ion, H3O plus, is the H ion in the water, in the aqueous solution. Look at this guy. Hydrochloric acid, H gives you a proton, and this proton reacts with the water, and the water basically will make this is an acid, this is a proton donated, and what happens now is it is forming a hydronium ion H3O plus, and the Cl will be left alone. So this is acid and the water. The, sorry for that. So this is the acid and the water. Now acid gives a proton to the water makes a hydronium ion, and the chlorine is left alone. Negative ion of chlorine, the chloride ion is left alone. So basic idea is that Arrhenius acid is an acid that donates a proton or an H ion or H3O plus. So I'm going to repeat again about the definition of Arrhenius acid and a base. So Arrhenius acid produces an H ion in the water. If you really look at this Arrhenius acid, HCl, H ion here, nitric acid, H ion here. So any substance that can give an H ion in the water will be called as an Arrhenius acid. Arrhenius base, on the other hand, produces the hydroxide ion. Remember your polyatomic ion and the OH ion which are negatively charged? So Arrhenius base is a substance that is categorized by giving you an OH ion in the water. Like look at this, sodium hydroxide giving you Na plus and the OH ion, hydroxide ion. Calcium hydroxide giving you calcium 2 plus and the hydroxide ion. So the NaOH and calcium hydroxide, both producing AOH ions in the water, are categorized as bases, Arrhenius bases. So I'll repeat, Arrhenius acid producing a substance producing the H ions in the water, Arrhenius base, the substance producing the OH ions in the water. So while Arrhenius definition was good to start with, but as the understanding of the acid and bases kept on growing, then the definition, this Arrhenius definition was limited. Because of the two reasons, it only would be true for the solutions in the water. So it was limiting the number of substances that could be categorized as an acid or a base. So then came two more scientists, Bronsted and Lowry, that gave a new definition of acids and bases. Because sometimes the chemists perform reactions in the solutions that are not in the water, and RNA's definition was only the substance that was in the water was categorized as an acid or a base. So for these non-aqueous solutions, how will you categorize them as an acid and base was given by Lowry and Bronsted. So the new definition came in, and what is this definition? So Brownstein and Lowry theory defines acids and bases as either a proton donor or a proton acceptor. So they gave the definition not in the terms of the H ions and the OH ions, but they gave the definition around the substances that can donate a proton or accept a proton. So according to the theory, the acids are proton donors. So let's look at this reaction. I have a substance HCl reacting with the water. Now these guys, how will we define them? Which one is acting as an acid and which one is a base? We have to look at the products. So if you really look at the HCl, HCl has become a chloride ion. So HCl has donated an H ion, so will be categorized as an acid. And water on the other hand has accepted this proton and has become a hydronium ion. So so water here was defined as a base. So the substance that donates a hydrogen ion is an acid according to Arrhenius, and the substance that accepts a proton according to um, Lowry and Bronsted is a base. Did I say Arrhenius in the earlier definition? I'm sorry, it is a Lowry and Bronsted definition. So the substance that donates a proton is a Bronsted Lowry acid, and substances that accepts a proton and makes uh, a compound in the product with an H, extra H is defined as a Lowry Bronsted base or a Bronsted Lowry base. So look at these guys. H donated HCl donated an H ion. It was accepted by the water. So what happened here was, um, again, this is a slide and I'm going to go over another reaction so that you understand it better. Or if I can go back again to the same reaction and let's see that the HCl donated a proton, so it's an acid. Water accepted a proton, so it is a base. Let's look at one more reaction and see Bronsted and Lowry definition. One more with another reaction. Look at this reaction, ammonia and water. Now, ammonia is accepting this H4 and this H3. So, ammonia has accepted a proton. So, it's acting as a Bronsted and Lowry base. And H2O breaking down into H and OH has become only OH. So, it has lost a proton. So, it's acting as a Bronsted and Lowry acid. So look at this guy. So water donated a proton, so it's acting as an acid, and ammonia accepted a proton, so acted as a Bronsted and Lowry base. So the formation of ammonium ion, it is done by the accepting of the proton by ammonia. So this is acting as ammonia is acting as a base. So this was the water. So this hydrogen ion or the proton was donated by the water to ammonia to make ammonium ion. So ammonia is acting as a base here because it accepted a proton. Water donated an H ion to make the OH. So water is acting as a acid here. So this was a simple definition of Bronsted-Lowry acid and bases. It really covered many substances, most substances that were non-aqueous solutions. Now, according to Bronsted and Lowry, there were substances that can act as both acid or bases. Um, and they were called as amphiprotic or amphoteric. And if you really look at that example, the water is the most common Bronsted-Lowry acid or a base. It can act as an acid or a base. It depends upon what substance it is combining with. So water can donate a proton and water can also accept a proton depending upon the substance that is associated with. So look at here. This is a methylamine and this is a methylamine actually, and this is the water. Now water is donating a proton here to CH3 and H2 and making CH3 and H3. So water here as is donating a proton is acting as a Bronsted-Lowry acid. On the other hand, the water here accepted a proton from the acetic acid, that is the vinegar. So CH3COO lost a proton to the water, and water acted as a base and made a hydronium ion. So this was the Lowry and Bronsted base, and this was the Lowry Bronsted acid. So water can act as an acid or a base, depends upon what it is combining with, and that is the reason it was categorized by Bronsted Lowry as an amphoteric substance. It can act as both depending upon what it is combining. So here, if you really look at it, this CH3NH2 is making CH3NH3 accepted. So it is acting as a base, water acting as an acid. Here, this CH3COH, my Chiku, acetic acid, vinegar, it donated a proton here, so it's acting as an acid. Water accepted a proton, made a hydronium ion, so acting as a base. Now let's look at the conjugate acid-base pairs. What are they? And I'll go very slowly to like so that you can understand. This knowledge of conjugate acid-base pair is very important when you do the reactions in the oceans. That is what my main objective is for the next week's lesson. How the acids they ionize and they produce the H ions. So, an acid and a base, they differ only by one thing, and that is the proton H ions. And they can make the conjugate acid base pairs. So, look at this guy. This is a reaction. In the forward reaction, if you really look at this reaction, water makes an OH ions. So, water donated a proton, so it's acting as an acid. So, water acting as an acid, the the part on the product side that is made after the donation. So this is acting as an acid, the part will be the conjugate base. They only differ by an H ion. Ammonia, on the other hand, accepted the proton, made an ammonium. So ammonia accepted is a base, and what it made is called as a conjugate acid. So the acid goes with the conjugate base pair, and a base goes with the conjugate acid pair. I hope it was clear. So we'll do more reactions so that you guys understand what the conjugate acid base pair is. So on the reactant side will be the conjugate acid or a conjugate. On the reactant side will be acid or a base. And on the product side will be a conjugate acid and a base pair. Acid always goes with the conjugate base, and a base always goes with a conjugate acid. So why is that so? Because the forward reaction, if you reverse the reaction, then in the reverse process, whatever was, this was the acid, this was the conjugate base, so this will accept a proton. So that is the reason in the reversible reaction they go and paired up like that. So I will do more examples for you so that you understand the conjugate acid base pairs more. So look at these conjugate pair, they only differ by the H ions. So let me explain one more reaction so that you understand better what the conjugate acid base pair is and how do you designate them. So look at this reaction very carefully. Ammonium made ammonia. So H ions has been lost. So ammonium made ammonia. So this ammonium is acting as a acid, and water will be made a hydronium ion. So water will be acting as a base. What ammonium formed is ammonia, so will be categorized as a conjugate base, and water formed hydronium will be categorized as a conjugate acid. So if you really look at them, they were only ammonium and ammonia. There was a difference of only H ion. As it donated an H and made ammonia, it is characterized as an acid. Its counterpart is called as a conjugate base. So acid and a conjugate base, they go together. Base and a conjugate acid, they go together. Here water accepted the proton, made hydronium, so it's categorized as a base, and its counterpart, what it made, was categorized as a conjugate acid. Let's look at this other reaction. Acetic acid. Okay, let me finish up this guy. I will explain it to you. Now, no, wait. So, acetic acid made HCOO ion. So, it lost a proton. So, I can categorize this as an acid. The counterpart will be categorized definitely as a conjugate base. CN accepted a proton, made HCN. So, I will categorize this CN as a base. HCOO as a conjugate base, and HCN as a conjugate acid. I hope you got this idea. Let's try one on your own and identify acid, conjugate acid, and a conjugate base on your own. Let's take a pause for the video, and why don't you do this on your own and let's see what you get. So let's check the answers. Did you get the same things? And let's explain why you got the same thing or same answers. Water accepted a proton, made H3O, so it's acting as a base. And this guy, the counterpart of this, will be called as a conjugate acid. Base and conjugate acid, they go together. Carbonic acid, on the other hand, HCCO3, it lost a proton to the water, so it's acting as an acid here, and the counterpart is called as the conjugate base. Let's do one more reaction here. Again, pause and identify acid, base, conjugate acid, and a conjugate base. Let's see if you can get it. Yep, acid, base, conjugate base. So HCO3 is losing and making CO3. So is acting as an acid. The counterpart is conjugate base. Water, on the other hand, accepted the proton and made H3O, so base and a conjugate acid. I know it is a little bit complex, but once you practice these guys, um, you will get the concept of conjugate acid and conjugate base, and I'll add more resources for you to go over the conjugate acid base pairs. This concept is very important when we do the ocean acidification. So, if you really look at that, the carbon dioxide from the atmosphere is entering into the hydrosphere in the ocean, making carbon dioxide reacting with water, making carbonic acid. And this carbonic acid ultimately dissociates to give you the hydrogen ion. And that is the ultimate goal, that like go over the objective that I was talking about. Acid bases have not been mentioned in your objective, but they're very important so that you know how are we getting the H ion in the oceans. Um, I'll come back to that, the H ions in the ocean, but let's change the gears and talk about the pH scale. You have heard about this pH scale a lot. Let me review with you. It is a scale that we can use to distinguish between an acid and a base. pH, P in the pH comes from the German word potens and the Danish word poteness, which means both of them means the power of H. And the H, of course, stands for hydrogen. The pH scale goes from a 0 to 14, the 7 being categorized as a neutral, and 0 to 6.9, the substances are categorized as an acid. 7.1 to 14, the substances are categorized as a base. So if you really look at these, all the fruits, the lemon juice, the stomach in your acid, the coffee, the milk, all of these are acids. The egg, the baking soda, the cleaning agents, all these guys are bases. The lower the pH gets, the stronger is the acid, and higher the pH gets, stronger is the base. So basically, what is pH measuring? pH is measuring the concentration of the H ions in the solution. Greater the H ions, the lower is the pH and more acidic the solution is. So pH is measuring how acidic or the pH the solution is, or how acidic or a basic the solution is. So really look at this. So the pH of 7 being a neutral water, and what I mean is if you go in this scale, if you go towards the left, you are becoming pH is going down, the solution is becoming more acidic. And if you go towards the right, towards the 14 scale, up the number line, it is becoming the pH is increasing and it is becoming more acidic. More basic. So lower the pH, more acidic, higher the pH, more basic. One way to determine the pH is by using the universal indicators. This paper undergoes a change in the presence of hydronium ions or the hydroxide ions, H ions or the OH ions. and the final color of the pH is indicated or is matched with the this wheel and with the colors in the chart, and you can tell what the pH of the solution is, and you can also indicate whether it's an acid or a base, like this. Like if it is a pH of 7, the color is green. If the pH of 1, it's a red, and it is an acid, a strong acid. We also use a pH probe to indicate the pH of the solution. It is like a digital litmus paper. It is immersed in the solution and it tells you a number, and that number is matched with a scale. Here it is showing 8.79. That means it is a basic solution with a pH of 8.79. This is the way we test it out, much easier way, because you do not, some colors can be very closely related and you cannot get whether it is 8.79 or 9. So the digital probe is much better. So let's go over the summary of acids and bases. Acids can form the hydronium ion or the proton or the H3O plus or the H ions when they ionize. Bases in the term, they form OH ions when they ionize. The above two theories are for from Arrhenius. Arrhenius acid produces the H ions. Arrhenius base produces the OH ions. Lowry and Bronsted acid is a substance that donates an H ion. Bronsted Lowry base is a substance that accepts a H ion. Conjugate pair differ only by the H ions. pH is a measure of how many H ions are present in the solution. An acid is a substance with a pH lower than 7. A base is a substance with pH greater than 7. And a pH of 7 is neutral. So this is the topic that we are going to go over the next week, or actually the few weeks from now. And that's why we went over the acids and bases for you. So look at the carbon dioxide molecule that is coming from the atmosphere. This carbon dioxide molecule is going in the hydrosphere, in the water, making carbonic acid. This carbonic acid H2CO3 is dissociating into the H ions and the bicarbonate ions. And these H ions is increasing the acidity in the ocean. What is going to happen when the acidity goes up? Some of the fish, the marine life, they are not going to like it. They like a certain pH in the ocean, and so the acidity goes up, the H ion goes up. It can harm the shells of the fish. It can harm the fish itself, and the population might go down. So there are additional resources for you. Um, that will help you out to understand the concept. They are actually optional, they are not mandatory. You have a video that will help you how the CO2 concentration is increasing in the atmosphere. Look at this. um, Go over this video please and see how the oceans are getting acidified. Then you can also go over the resources on acids and bases, their properties, and there are other PBS videos that will show you about the pH scale, indicators, and acid bases. I hope you enjoyed today's lesson. Thank you. Enjoy your day and finish up your assignments, both assignments that we talked earlier. There are two Google Forms to go with this, one on the simulation that you're going to work on and complete the Google form, and the other one is the slideshow that I just went over, and both of them are due by this Sunday. Thank you so much. Sorry for the phone